Hi again. We're back, week 7, moving into a sort of transition chapter of sorts. We're getting close to the end of actually mechanics. But this is a little useful piece that I hopefully can show you connects up some other ideas we've tossed around. And it's all about the context of work and of energy and then the beginnings of the notion of a field, that conserves energy. And we'll come back to fields more in an electrical setting, but this hopefully will be the introduction to it. Now, the background for this, you recognize, this is about pressure volume loops, which we showed you how we derived from the Wiggers diagram. And we even described what happens when we get an increase in the filling volume into the ventricles, into the heart. We call that, in sort of more physiological terms, we call that a preload. So we load the heart with more volume. We shift the curves over to the right, as you see here with the different colors. And that causes a more forceful contraction from the heart just because of that filling. And that, of course, was the Frank-Starling's law, or the Frank-Starling mechanism. That was also contained by those two dashed lines that you see there that hopefully you remember are really the compliance of the ventricle in its two different phases. So remember, we had a diastolic compliance and a systolic compliance, and those curves operate between those two lines and follow their tracks depending on the local response of the heart. And that's the story we've heard already. But there's more to control of the heart than that. And I want to talk just very briefly about that because it's useful to put it in context. So we know the brain regulates the heart. We've talked about this in the discussion section. We even described a scenario in which the brain wasn't connected to the heart and we had to examine what other regulatory mechanisms there were. But when the brain is connected, we have what's called the autonomic nervous system, or ANS, in place, and it contains two branches, or that's how we describe it. One's called the sympathetic, one's called the parasympathetic, and they're opposing in their actions. Sympathetic is what gets cranked up, what gets stimulated when we're in flight. It's called a fight or flight response. So when we're in an aggressive situation, a fear situation, and sometimes even a sports situation, then the sympathetic stimulation increases. And that has effects all over the body. You'll learn lots more about that in physiology. But it has profound effects on the heart. Now, the parasympathetic is the opposite. It has a slowing, calming, reduction of contraction kind of effect on the heart. That literally slows our heart rates down. In fact, our heart rates are chronically slower than they would be if we just had an intrinsic rhythm, let's call it. If we were to, as bizarre as this sounds, have our hearts removed, let's say we were donating and had a terrible accident, our hearts would slow down in our bodies and then, of course, speed up slightly if we took them out of the body, because then we'd no longer have this autonomic control that chronically slows down the heart. So that's parasympathetic, sympathetic, part of the autonomic nervous system. And again, you'll hear a little bit about them in this course, a lot more in the future. Now, what is the effect of these autonomics on the heart? Well, again, we can go back to our pressure volume curve, which describes the scenario, describes the action of the heart. And we can picture what would happen, say, during exercise. We talked about this a little bit already. There we have stimulation through Frank-Starling, but also stimulation through the autonomic nervous system. Our sympathetic nervous system goes up, our parasympathetic goes down. So we remove that inhibition, enhance the heart rate, the contractility, and that's how we're able to achieve those very high cardiac outputs that I mentioned in a previous video. And that looks something schematically like this. When we have exercise, the pressure goes way up during contractions, the contraction is more forceful, the stroke volume is increased quite dramatically. So in summary, we have the brain controlling the heart, superimposed on top of the Frank-Starling mechanism that we saw during heart transplants, a mechanism we described already. And then there's a third component. Again, I mentioned just briefly, because it did come up in our discussions about how hearts are regulated when a recipient gets a donor heart. So when a patient has such a sick heart that they need a heart transplant, they receive a heart that is never connected to the nervous system again. So how does it get regulated? How does it control speed and contractility, cardiac output? Well, it does it through the Frank-Starling mechanism we've heard about, but it also does it through what's called the endocrine system. And the endocrine system is an indirect control from the brain to many organs in the body. The endocrine system affects all sorts of things. These are where hormones come from. That's the substances that the endocrine system actually dumps into our blood supply, and then the blood transports those substances to the organ that's affected or the system that's affected, in this case to the heart. So we have the adrenal gland specifically that is controlled by the brain and releases adrenaline, that substance you've heard of before. And that adrenaline, when it goes through the blood to the heart, causes the heart to beat more forcefully and even beat more rapidly. And so we have control of the heart. So the heart sits in the middle here, if you will, and it has input from the brain, input from the endocrine system. It also communicates back the other way to those two organs. The two vagus and sympathetic nerves you see from the brain, they control the two arms of the autonomic nervous system. And so there's a whole communication that goes on here that, again, you'll learn a lot more about in physiology. But that's the high-level picture of how the heart's controlled. You're going to be replicating some of these behaviors and influences with the major project. You can replicate an increase in or release of adrenaline that causes increase in contractility or increase in heart rate, factors like this. So I wanted to know where they all come from before we start including them in your models. So now we switch focus again, sort of a short topic that we cover briefly in chapter 7, and that's work. We need to talk about work. I know work's not always the most pleasant thing to do, but we need work. We need to do work or else we don't live, quite simply. And so how does work play out in the heart? Well, work plays out, as I mentioned before to you, directly visualized in a pressure volume loop by the area under that loop. And we'll explain a little bit where that can come from mathematically, but the point is that we have a volume, a change in a space dimension, and then we have a pressure, that's a change in a force type quantity, pressure being force over area. And so that area together within the PV loop for a heartbeat tells us how much work the heart actually performed. And as I said before, it's a valuable metric of the heart's behavior, its performance, its status, if you will, for clinical evaluation of that heart. And that's work. So we have a vague idea what work is about, but how is work related to energy, and how are energy types related to each other? That's really what we want to get to, because we know when we go up a hill, walking, hiking, riding our bikes, we gain potential energy that allows us then to go down the hill. And then we transfer that potential energy that we got by gaining elevation into kinetic energy, which translates directly into velocity. And you've hopefully seen this in physics. Hopefully this fundamental idea is not new, but we're going to apply it in a biological situation. So another thing you've seen before is that work essentially is force applied over a distance. So we've seen this equation hopefully before, the dot product between force, which is a vector, and the movement, which is also a vector. Also written with the cosine function, so there can be an angle between the force applied and the actual motion. We see this object being pulled across a plane. We can turn that plane up on its edge, and that changes the angles and changes the work, which is why it's harder to go uphill than it is to go level. So we've seen all this before. But what's the relationship between work and energy? We sort of throw the terms around maybe a little bit too loosely. One summary I found was that energy is the currency of work. So energy is what passes back and forth, like money passes back and forth in a transaction. So energy is that currency that allows us to do work, or that allows work to be done on us and all these sorts of things. We need energy to perform work. That's another way to think about it. We need energy in the form of food in order to perform work that we do as physical exercise. That's another way of thinking about it. And then finally, work changes the energy state of a system. So a system is in a certain energy state. You can picture this really simply as in you're at the top of the mountain, you're at the bottom of the mountain. And you're at the top of the mountain, you have higher potential energy. That's your energy state. And it takes work to get you to the top of the mountain, your work, the work of a cable car, whatever. You have to, somewhere work has to happen in order for you to gain that energy. So work is a function, or not a function, it's a quantity, it's a substance sometimes, but it's a quantity physically that allows the energy state of a system to change. So again, we use this energy as the currency of the work we performed, which then changes the energy state. So this is why it gets all convoluted. And so you just have to sort out which means what in what context, because they're not always consistently used words. So how do we describe energy in terms of equations? So this one, hopefully you've seen before. This is the equation for potential energy, which is the energy an object has because of its altitude, its height, and its energy that's ultimately derived from gravity. So the force applied on that object that's holding it down is gravitational. If we fight that gravitational force with another force, we can bring energy into the system. We perform work to bring energy into the system. We expend energy to bring that work into the system to improve its energy state. So this is where it gets all convoluted, but I think you understand the basic idea of potential energy. It's potential. It's energy that can be released when the conditions allow. When it's released, it gets converted into kinetic energy, the energy of motion. This is the velocity term, a velocity squared term, in fact, that characterizes the amount of energy that a moving object has just through its motion. So any object moving has kinetic energy. And there's a transfer back and forth between these two forms of energy. And there's a notion in physics, here we go again, a conservation law. This time, physics tells us that energy is conserved. So that if we gain one type of energy, we lose another type, so that the total sum of energy of a system is the same. And if we want to change that energy state, we have to do work on the system. We have to bring external work to change the energy state of the system. Now, one of the curious things about this that may not seem intuitive at first, but is true in the purest physical sense, is that the energy is truly, in this case, a function of just altitude. When you think about that and think about how do I get from one place to another? How do I move from a place of low altitude through a path to a place of higher altitude? And what if I do it a different way? What if I take another path that's maybe even longer and has a different route? Maybe it goes up a different part of the mountain. Maybe one part's up a steep side of the mountain, one part's up a less steep side, but it takes longer to gain the same altitude. According to physics, the energy gain, the energy state, the potential energy we have at the top of that elevation gain is the same. That energy difference is the same, no matter what route we take. And that's a pretty powerful concept when you think about it. And if you think about it and imagine where you've gone hiking before, where maybe you've taken two different routes to get to the same spot, you'll question that. You'll wonder, wait a second, it didn't feel like I had to perform the same amount of work to get myself into this new energy state. It may feel that a steeper slope is harder, and it may feel like the slower, longer route is less energy consuming. And this is real, and we're going to talk a little bit about that, because we need to think about this in the context of our daily lives, of walking around mountains, riding our bikes, going on the Bonneville Shoreline Trail, and trying to picture what goes on. So here's a specific example. So here's a map, obviously. This is a map of, guess what, the university and part of Salt Lake City with the hills, the foothills above it. Now, we'll zoom in on a little bit here. And if you look really closely, and if you know your way around up there, you'll see the Bonneville Shoreline Trail route, and you'll also see a very famous mountain bike route, primarily mountain bike route, called the Bobsled Run. A number of you have probably ridden. Now, we can go from the bottom to the top of the Bobsled Run at least two different ways. One of them looks something like this, where we kind of go out to the side and use the Bonneville Shoreline Trail to get to the top. And one of them is we start at the bottom of the bobsled run and we go straight up that run and we get to the same place. We have gained the same amount of potential energy. And the question is, what's the difference between those two? And how do we explain that? How do we explain that difference? Because physics tells us that energy is conserved and that we had to burn the same number of calories or extend ourselves to the same extent, however you imagine quantifying that, to get from point A to point B in this case, independent of the route. Independent of the route. And that's a very powerful concept we need to think about. So another way to think about that is energy conserved? Is mechanical energy conserved? So the energy I put in to get up that hill, is it truly all available to come down that hill? If I go up a hill a certain distance, let's say I ride my bike up and I come back down to the bottom of that hill, and I take all that speed and I go up the other side of a hill, will I get to the same altitude again? That would be conservation. I'd be able to yo-yo back and forth. If I had a sort of U-shaped segment of road, I'd be able to yo-yo back and forth and always go back to the same height. Now, practically, we know that doesn't happen. And so we have to think a little bit about why that doesn't happen and where that energy gets lost. Because if energy is not conserved in terms of our potential and kinetic energy going up and down the slope, it's got to go somewhere. Because energy truly is conserved. It just changes form. We have energy losses that have nothing to do with the altitude that we've gained, that would slow us down but still bring us to altitude. There are many other factors that are energy suckers, energy sinks, energy losers for us. And they're why every time you go back and forth, you'll go lower and lower and lower and lower every round, unless you put more energy in, unless you crank those pedals a little bit. So we think about this in terms of efficiency. Now, that's another very important word in engineering. We all try to be efficient. Colloquially, in our lives, we try and be efficient. But energy systems, we can also use the word efficiency to describe. And so here's a nice image I like that has the body in the center of it. That's us. And we have sources of energy intake. So that comes from the fuel that we eat, literally, the air we breathe, the oxygen. That's metabolized and turned into mechanical energy. And some of that mechanical energy goes into moving us around on our bikes or our legs, and we can transfer that between potential energy. We can have kinetic energy. We can go back and forth between those, depending on what our motion is. And there's all sorts of rapid energy and slow energy. Growth is a form of energy. We need growth to get bigger. And when we get bigger, we've changed our energy state, and we need input energy to deal with that. Now, of course, we have losses, we have inefficiencies along the way. The thermal losses are the ones we notice most when we exercise. We get hot, we get sweaty. So that's a thermal energy loss. If we're on a bicycle, what else could we lose? Well, we could lose energy through frictional forces. The bearings in our bikes, the chains maybe that are driving the bikes, the wheels and their contact with the road surface, all those things take energy out of the system. There are losses in this system. And so we try and capture this notion of efficiency in some kind of ratio. And there are different ways to frame efficiency. There's not a fixed formula for this. It's something you have to kind of apply selectively and carefully and openly and say, here's my measure of efficiency. And here's sort of generically what we think about as efficiency is the amount of useful work we achieve, whatever that may mean in a given context, compared to the amount of energy we consume to get that useful work done. Now, of course, in a perfect scenario, all of the energy consumed would be turned into useful work. We'd have a 1-to-1 or 100% efficiency. But of course, that's not how it happens. We achieve much less or somewhat less useful work than we actually put into the system. And that's one metric we can use to think about efficiency. Now let's think about efficiency in terms of movement, because we're in this mechanical domain. We're going to talk about biomechanics very soon. So here are a number of modes of transportation, of getting us around. And we see, from cars with a single person inside that car, all the way through multiple riders, moped, motorcycle, walking, running up to bicycles. So what am I doing here? So on the x-axis, we have calories consumed, kilocalories consumed per kilometer of travel. So that's kind of a notion of how much energy it takes for a kilometer of travel. That's already an efficiency metric, but that efficiency changes with mode of transportation. So you see the car is the least efficient, the horse and the swimmer not very efficient either, compared to the walker and especially the cyclist. Now, within those categories of the different modes of transportation, we also have differences related to speed. It turns out that our efficiency changes as our speed changes. And if you look carefully, you'll see that as the speed goes up, we move down that scale. As the speed goes up, we see that on a bicycle, for example, our efficiency, our consumption of food, let's say, or the calories we consume to achieve that speed, that actually grows. So we become less efficient as the speed goes up. And you say, well, why would that be? Well, if you think about it, of course, we're going faster, we're going into the wind. Wind resistance plays a bigger and bigger role the faster we go. And it's not even a linear relationship. It's a vaguely squared relationship, or at least that's how we model it. So efficiency is a key concept, and we can take the numbers out of this graph, and if you're the numbers I dug up, and we can determine that, for example, we can look this up, a gallon of gasoline, let's use that as our common energy denominator. The energy in a gallon of gasoline is something like 31,000 kilocalories. We're metric, so we're going to divide that and get liters, and we get something like 6,800 kilocalories per liter of gasoline. And it turns out that if you do the conversions, miles to gallons and all that good stuff, you get something like 6 to 12, something in that range, kilometers per liter of gasoline in a contemporary car. So that's sort of the cost, if you will, or the actual efficiency of the number of kilometers per unit of energy. That's another metric of efficiency. Now we look further up the scale and we say, what about the walk or the runner? Well, there, the energy of running and walking is something like 3.78 kilojoules per kilogram per kilometer. So mass plays a factor here, of course. The heavier you are, the more energy needed to move you as you're a runner or a cyclist. So approximately here we did a 68 kilogram person. We end up with something like 58 kilocalories per kilometer. That's what the expenditure is. It's what the energy cost is of moving along the road at some moderate speed. Now that means that if we could consume the energy of a liter of gas, we could do 117 kilometers on that 1 liter of gasoline. So rather than the 6 to 12 kilometers, we could go something in the order of, let's say, 100 kilometers to 120 kilometers, depending on the runner, the speed, the efficiency of the runner, all those sort of good things. Now, if we go to bicycles, of course, it gets better still, because bicycles are the most efficient way to get around. And here we see that we only need 1.62 kilojoules of energy per kilometer per kilogram. And that all translates into, for again, a 68 kilogram person, same sort of size person as before, we get 272 kilometers on a liter of gasoline. So that puts in some kind of terms just how dramatically more efficient a bicycle is, how much less energy needs we have to gain the same distance on a bicycle than other modes of transportation. Now, these efficiency numbers we can think about throughout our bodies. They come up again and again. There's lots of different ways to measure them. And it's at this point more this sort of overall notion of thinking about, efficiency is a factor. How efficient is my body? How much energy can I consume from the kilocalories worth of food that I consume? Because we can analyze food, determine its caloric content, which is another way of saying its energy. We can say how much that apple has in energy or how much that candy bar has in energy. And we can say how much of that energy do we actually turn into useful work. And that's another form of efficiency. And it's not that high in humans, as it turns out. 20%, 25%. It's not an encouraging number. But it does allow us to eat more. That's a good news story for this, for sure. Okay, so there are other forms of physiological energy you'll learn more about in the setting of physiology. I won't go into those. There's that we have an energy system in our body. There's so much to learn about this, metabolism, all the factors of energy that affect our bodies. It's a rich vein of knowledge and research to understand metabolism, how energy is managed in our bodies and how it's transferred, and all these many diseases that are related to this. So it's an important and rich area that we're not going to spend a lot of time talking about here. Just more to think about this overall question of efficiency and also of conservation of energy, this notion of conservation. Because in the next video, I'm going to describe an experiment that I've been working on all summer long, in which I asked the question, how well is that notion true, or how true is that notion that if I leave one altitude and go to another altitude, that it's independent of the route, even if I use the same mode of transportation. So I use the same efficient mode of transportation. I use a bicycle and I go between two routes. And the route looks like this. The video will explain this in more detail. The profile, the length, the statistics of the route look like that. And the question that I want you to think about, especially as you watch this next video and as we head into the discussion sections this week, is what do you think the outcome was? Which one of these two routes between 2 points do you think took more time or took me more energy, more work? I can estimate at least, or a program that I use for this can estimate how much my average power consumption is, or my power expenditure is. How much work, how much power did I put into the pedals, so to speak, to move myself on the bike. So that's a power estimate that we can also use. And that's sort of the physiological physics question. But then I want you to think about the experiment as you hear about it, and then we'll the next video will tell you roughly what I did. And then during the discussion sections, we'll get into some of the details and I'll share some of the data with you. But first I want you to, think about it, anticipate which route do you think was longer, which one took more energy, what would the difference be? Again, given this particular picture of a certain distance, a certain average grade, a certain profile. Both these routes are quite different in that regard, but they do start at the same altitude and end at the same altitude. They do literally start at the same 2 points and end at the same points. So think about that some more. I'll sign off for now and watch that second video so you have an idea what I did, a little more of the experimental details, and then we'll talk about it in the discussion sections this week. Thanks so much. Take care. Bye-bye.